So we're going to start off by going over the exam. I'm going to log on to Blackboard as if I were going to take the exam. And the exams are non-cumulative. So now that you've gotten through this one, you're not going to have to go back and take a look at this again, although the material builds on this stuff. So there is a little bit that you're going to have to remember from this and maybe reapply in a different form. Okay, so let's see what we have. Make sure I can't make this a little bit bigger so we can see it. How do we feel about the any surprises there in that list of variables, right? Ethnicity, pain scale obviously is a ordinal scale, numerical, mother's age, numerical, gender, newborn, nominal, and so on and so forth. I don't think there's any real surprises there. If you guys online have any questions there, let me know. Okay, the histogram always seems to make people uneasy. Did you guys here have any trouble with the histogram? No? No? Okay, good. Yeah, the only thing that might be a little bit of a curveball is this idea of conditional probability. Given that a patient has stayed for 11 days or more, what's the probability that that patient stayed for 14 days? Right? If you look there, 11 days or more would be the histogram, the frequencies on the right-hand side. So 2, 2, 7, 9, 10. Do I have that right? Is it 10 or 11? 2. Oops. 1. Back away. 2 and 5, 10. Okay, and there's only one person that stayed for 14 days, so it's 1 out of 10. So we're only considering the condition that has been satisfied, that 11 or more. Was probably staying in center for fewer than 8 days. Exactly. Just that's pretty straightforward. Okay, how about the diagnostic tests? Any surprises there? Nope. Okay, let me just go over that quickly. What's the prevalence of disease in this population? Well, we have 1,000 people, right? We have 100 people out of those 1,000 that actually have the disease. The sum of those who tested positive and tested negative who had the disease, in other words, the true positives and the false negatives. 10 would be false negatives, they tested negative, but they do have the disease. So 100 people in this population have the disease, and there's 1,000 people in the population or in the sample. So the prevalence here would be 10%. Point 1, what's the sensitivity of this test? Well, sensitivity, it tells us how good it is at actually identifying people that have the disease. So out of the 100 people that actually have the disease, it correctly identified it in 90 of them. So the sensitivity is 90%. What's the positive predictive value of disease? Well, the positive predictive value is tied into these positive tests. Everybody that's in this top row has tested positive. These 90 have tested positive and have the disease. These 198 have tested positive, but they're negative. They don't have the disease. So was there a question? Did I skip a question on the specificity? I guess I didn't ask it. Okay. So the specificity of this test would have been the number of people we correctly identified as not having the disease over the total number of people that don't have the disease. So the true negatives over the total number of people that are negative. So that's 702 over 900. So that would be, what would that be? 85% or something like that. What is that? Even though I didn't ask that, I just want to make sure that we understand that. 702 divided 900 equals 78%, it looks like. Am I right about that? Okay, good. So that kind of an oddball specificity, right? So the total number of positive results in this test are 288. Only 90 of them were actually people that had the disease. So if you're among those 288 that tested positive, your chances of actually having the disease is only 90 over 288, whatever that comes out to. Consider a diagnostic test for cancer that is 99% accurate on individuals with cancer if an individual has cancer. The test is 95% likely to produce a positive test, hence the definition of sensitivity, and it's 90% accurate for individuals without cancer. Produces a negative result in 90% of healthy individuals. This test is then applied to a population with a prevalence of 1%. If an individual receives a positive test, what is the probability that the tested patient has cancer? No, probability is a decimal number, and so on and so forth. Okay, so you guys remember the formula for Bayes' theorem? Do you have it handy? Is this one of the ones that was an issue?
Yeah.
Okay, good. Okay, good. Let's take a look. Oh, I don't want that first. Well, there's a couple of ways you could have done this. I'm gonna take the formula away. Nope. Come on, let's see if I can't find one here yet. Nah, I don't want that formula. It's in the homework. I know that. I'm gonna Google it. Just easier. I'll use Google. Let's see, image results. This is going to make me unhappy that I used Yahoo. Let's see, I just saw it come up. How about this one right here? Here we go. This should do. I don't know if I got that. Okay, I'll be able to keep that open now. Okay, the positive predictive value is equal to the sensitivity. Basically, if you look at this carefully, what it says is the sensitivity times the prevalence. The prevalence is the percentage of people in the population that have the disease, right? So that would be, in this case, it would be 1%. The sensitivity is how good this test is at identifying people that have the disease. So if the prevalence, I'm going to change this, if the prevalence had been 50% and the sensitivity had been 90%, then 90% of those 50% of the people would have been correctly identified as having the disease. So these are our true positives. The people that have the disease, 50%, 10%, whatever percent of the population, times the percentage of people that get tested and are correctly tested. So these are our true positives. So on top, we have our true positives. On the bottom, we have our true positives again, plus, and if you look at this carefully, it's going to wind up being our false positives. The people who don't have the disease that are incorrectly identified as not having the disease, and these are false positives. So what we have here really is the true positives over the total number of positives, which is exactly what the positive predictive value is. But that given, let's take a look at what we would have to do to solve this. Okay, so the prevalence is 1%. The sensitivity is, what was it? 99%. So we got 0.99 times 0.01. And then we have 0.99 times 0.01 again, plus 1 minus the specificity. What was the specificity? It was 90%. So this would be 0.1, 10%, times 1 minus the prevalence, which would be 0.99. Okay, so if I fill in all those numbers for you like that, you should be able to solve that, right? So I'm not going to solve that. I'm going to take a look at this a slightly different way. Okay, and I'm going to set up a box over here. In case you don't feel comfortable with that formula, you can just fall back on making up a sample population and just solving it the way we did all the other stuff. Okay, so let's see. Here we go. Oh, this is pretty ugly. Okay, so this is positive test. This is a negative test. This has the disease. this, oops, this has a disease, this doesn't have the disease. And these are the totals otherwise. So 1%, the prevalence is 1%. So I'm going to make this 1,000. If the prevalence is 1%, how many people out of those 1,000 have the disease? 10, right? 1% of that 1,000 is 10. So 10 people have the disease. Okay, how many people don't have the disease? 990. Okay, so everybody in this column, out of this 1,000 people in the population, has the disease. So 10 people out of that column, out of this column. 990 people don't have the disease. Everybody listed in this column doesn't have the disease. Some of them test positive, some of them test negative. So what was the sensitivity? What did we say the sensitivity was? 99%. So actually, you want to know something? I'm going to make this 10,000, make this 100, and make this 9,900. Okay? I'm just doing that to make the number. I could have just kept going the way I was going, but I'm going to wind up with fraction, decimal, so I don't want to bother with that. Okay, so if we have 100 people, which is 1% prevalence out of 10,000, we have 100 people who have the disease, and the test is 99% accurate at identifying them, well, then 99 out of 100 would be correctly identified and test positive. Only one person out of 100 would test negative, right? So this is true positives, and this is false negatives. But all these people are positive. So we have 9,900 people in this population out of 10,000 that don't have the disease, right? So what was our specificity? 90%. Equals 90%. So 90% of the time we'll get this right. So I can multiply 9,900 times 90% and put it in here because they'll test people who don't have disease or should test negative, and 90% of these people will properly test negative. But tell you the truth, it's easier to just take 10% of that and put it up here because we'll get it. If we get it right 99% of the time, we're going to get wrong. 90% of the time, we're going to get it wrong 10% of the time. So I just wrote that up there because it was easier. So what does that leave us here? That leaves us with 8,910 people, if I'm right. Right? I think I'm right. And am I right about that? Yes, I'm right. Add these up. 0, 0, 0, 9, and 9. 18, carry the 1 is 9. Yeah, that's right. Okay, so how many people tested positive? Right, well, the total number of people that tested positive was 1,090 less 1,090, 1,089. Total number of people that tested negative was 8,911, and those should add up to 10,000. They do. So what is our positive predictive value equal to here? It's the number of people that remember, our positive predictive value is the probability that you have the disease given that you've tested positive, right? So let's see. This number of people tested positive. This number of people tested positive actually have the disease. So it's going to be equal to 99 out of 1,089. Okay, and if we do the math there, it's going to be 99 divided by 1,089, and that's equal to, it's going to equal to about 9%, a little bit more than 9%. Okay, so you have a 9% chance of having the disease in this test, even though the test has a sensitivity of 90%, 99%, and a specificity of 99%. If you test positive, there's only 9% chance you actually have the disease. Why is it so low? What makes it so low? What's the one thing here that really makes this particular, one factor in here that really affects the positive predictive value? The prevalence, exactly, because there's not many people in this population that have the disease, right? That means that you're going to have a lot of people that are negative that are going to wind up being thought to be, they're going to wind up getting false positives. So even though the sensitivity is excellent, and even though the specificity is not terrible, it's just that there are so many people that you're testing that don't have the disease that you're obviously going to wind up with a lot of false positives, right? And that's true for a lot of diagnostic tests, right? Because a lot of times, diseases that's important to get an early detection on, doctors are encouraged to do the test, even though the likelihood that you might have it is relatively low. And this is always a trade-off. I mean, these 1,089 people might have had to go on for more invasive tests, for more expensive tests, and so on and so forth, even though the probability of them having the disease was pretty low. Okay, so let me just do this while I have it out. See if we get the same answer. I probably, I'm saying to myself, I got away with this without making a mistake. Why would I do this now? Okay, but I'm going to try it anyway. Okay, the sensitivity was 0.99 times the prevalence was 0.01 over, over 0.99 times 0.01, right? This is all the true positives, plus the 1 minus the specificity, which was 1 minus 90%, which is 10%, times 1 minus the prevalence, which was 99%, which was 1%. So that's 1 minus the prevalence is 99%. What was this? Okay, good. Okay. Do I get that right? Yeah, I got that right. Okay, so what does it come out? On the top, we got 0.99 times 0.01. Move the decimal place over 2 places, so it's 0.0099 over 0.0099 plus 10% of that is 0.99, right? The opposite, I'm moving the decimal place over 1 place there. So that's going to be equal to 0.0099 over, and now I need to add these two together. And how am I going to do this without getting this wrong? 4 places, so this is going to be 9. 9 and 9 is 18, carry 1. Do I still have a 9 here? Or just, no, I just got 0.10. Okay, so, it's the same thing. Isn't that the same number? The same numbers we got before, except with decimal places. So it's going to come out to the same thing. It's going to come out to 9%. Hallelujah. Okay, good. So I rolled the dice, still got it right. All right. So you could have done it either one of those two. In fact, if you really were nervous and you had a lot of extra time, you could have tried both ways, just to make sure it was right. Okay. I think the expectation was you're going to try it the other way. Which of the following would provide the largest increase in positive predictive value? And it's really the change in the prevalence that would help us there. Higher, if you want an increase in positive predictive value, would be if you applied it to a population with a higher prevalence. Just the same way, which would diminish the positive predictive value, is if you applied it to a population with a lower predictive value. I mean, a lower prevalence, excuse me. Okay, let's see, binomial distribution. Oh, I helped you out there. I actually named what this problem was about. Okay, how about this one? A lot of people have issues with this one because I actually, be honest with you, now that I'm looking at this, I purposely put in binomial distribution as a title to this problem because so many people, the last time I asked it, had problems, thinking, well, instead of my saying that the probability in the population or the prevalence of population was this, it's a word problem instead. You have to figure. Yes, a lot of people had trouble with that. So I actually put in binomial distribution on purpose to key it. In any given year, 1 in 3 Americans over the age of 65 will experience a fall. So the probability of any single person in the United States over the age of 65 that you would randomly select is going to experience a fall is 33%, right? 0.333. Okay. If you have 3 living grandparents over the age of 65, that's your number of trials, that's your sample size. You have 3 people that you're going to apply this to. Assuming the probability for a fall of each grandparent is independent, what is the probability that none of the 3 grandparents will experience a fall? Well, okay. Now, if you're going to wind up using Excel for this, you can use the binomial distribution. You don't need to, right? Because didn't I just say that the probability of any one any one person in that population experiencing a fall was 33%, 33.33, right? What's the probability of not experiencing, and of one person, any one person not experiencing a fall? One minus that, 0.66, right? So what's the probability of all three not experiencing a fall? 0.66 times 0.66 times. So you could have just done it that way, 0.66. But if you decided to go the route of using the binomial distribution, okay, and that includes like waiting for Excel to open up or disappearing when you thought you opened it, or oh, there it is. Okay, let me get the view. Let's do that 250. Good. Okay, so let me give that a try. Equals binom dist. Now, there you go. Okay, parentheses. Okay, so it prompts us. The first thing it prompts us was the number of successes. Number of successes is 0. Want to know about none of them experiencing a fall. The number of trials is 3. You're applying it to your 3 grandparents, comma. The probability of any one of them having a fall is 0.333, comma, and cumulative, true or false. Which one do you think I should put? Yeah, I would use false as a fallback because we're only asking for that exact outcome just for habit's sake. To be honest with you, it doesn't matter. If you put true or false, you're going to get the same result because it's going to give you all the probabilities from 0 down. And since there is nothing below 0, it's not going to matter. In fact, let me do that. Equals binom dist parentheses number successes is 0, comma, 0.333. Oh, no, trials is 3, comma, 0.333, comma, true. Bing, same thing. Okay. So we've convinced ourselves of that. Good. Okay, according to behavioral risk factor, 58% of Americans adhere to a sedentary lifestyle. Assuming that the surveillance system is correct, what's the probability of finding 8 or more individuals who are sedentary from a random sample of, I lost it there, 10, 8 out of 10, right? So 8 or more. So that means the probability of 8, 9, or 10 satisfies that, right? So since the binomial distribution only works from one number of successes down, I can only find out what's the probability of 7 or less and then subtract it from 1. Okay, so I'm going to do that. Equals binom dist parentheses, and number of successes is 7, comma, and you see why I'm using 7, because 8 or more is what I want. So 7 or less is what I'm going to subtract from it. Trials is 10, comma, 0.58, comma, true this time, right? Because we want to get 7, 6, 5, all those probabilities. And then we just take 1 and subtract that value from it. The probability of 8 or more is about 14%. Okay. Using the file, high school athletes 2017, calculate the mean BMI for the sample. I'm going to use SPSS because I'm hoping that as we go forward, that you guys will get more and more comfortable with SPSS. I'm going to encourage you to use that. So I need to find that file. Let's see if I can't find it by searching rather than going back to, okay. Let me see if I can open it from here. Calculate the BMI for the sample, the mean BMI, using calculate the standard deviation, using calculate the interquartile range, side-by-side box plots, comparing, and that box just came up. I can't read that. I don't know what it's saying there. I don't know why it's saying that. And it didn't open my data file, did it? Maybe we couldn't find it. Let me try putting it on the desktop. Okay, it's on the desktop, so I'm going to do it the hard way. File, Serialization scheme. Boy, open data. Some interesting error messages I'm getting here. Data, my name, my user area, my desktop. Where's my desktop? Where'd it go? And here it is. Oops. Let's see if it opens this time. Oh, I got lucky this time. Okay, so what I'm interested in is this particular variable, this numerical variable, BMI. And I'm interested in the mean, the standard deviation for all of the girls in this survey, right? Not just in the sample, not just for one group or another, not just for the different sport, not for any particular sport, but for all of the girls overall. So there's a couple of ways I could do that. I could go to analyze, descriptive statistics, and I could go to descriptives. And I could say, let me find the right variable, numerical variable I'm interested in, move it into the variables box. Okay, options, I can check them off. Mean and standard deviation, it's going to give me those things, right? It's not giving me the interquartile range, that was it, right? So I'm going to click continue anyway, and I'm going to finish that up. Okay, and it gives me two of the three statistics that I'm interested in. It gives me the mean, and it gives me the standard deviation for all of the girls. Unfortunately, it doesn't give me the interquartile range. Well, there's two ways around that. I'm going to go back to analyze, to descriptive statistics. I can go into frequencies, or I can go into explore. I'm going to go into frequencies for the moment. Normally, I'd only go into frequencies for a categorical variable, to find out how many males or females there are, like frequencies, like a count. But I'm going to go in there for BMI, and I'm going to ask it to tell me, well, look at this, quartiles. So the quartiles, in a sense, are the interquartile, will tell us the interquartile range. I can also ask for the mean, the median, standard deviation, and so on. I'll click OK, and let's see what it brings up. Okay, well, first of all, since it's going to give you the frequencies automatically, you can see it's kind of a waste because the frequencies, the BMIs for every one of the girls is different. So actually, here we got two that were 19.9, but this isn't really useful to us. But it did give us another reading of the mean, the median, the standard deviation. And look, it gave me the 25th percentile and the 75th percentile. And the interquartile range is the difference between the 75th percentile and the 25th percentile. You guys okay with that? Okay. Try another way. Analyze, descriptive statistics, explore. The reason why explore is really valuable to us is because it allows us to factor the categorical variables into their different values. But we don't have to use it that way. We can still tell, just through these, just calculate the statistics for BMI. Incidentally, it's going to calculate a confidence interval for you. Remember, that's one of the things we've been working on is confidence intervals. It's going to calculate standard deviation, standard error, the p-value, and a confidence interval for you, right? If automatically, if this is this way, 95% by default, or you could change that to 99 or 90 or anything else you might want to use. So I'm going to leave it just like that. And if I click OK, you'll get a much more extensive list of statistics, I think. Here we go. There's your mean, your median, your standard deviation, and your interquartile range, your minimum, maximum interquartile. So that's another way you could have gotten the interquartile range. And then finally, the last question that drew on this data set was, and I'm going to go back to this, produce a table comparing the mean, standard deviation, other statistics of the BMIs for female athletes who participate in aerobic versus non-aerobic sports. Produce side-by-side box plots and copy and paste the tables and so on and so forth. By the way, I'm not asking you to copy and paste the tables because I'm trying to be mean. I'm trying to do it because I want you to be prepared to actually use this stuff usefully. In other words, if you go on to EPI and they give you a data set, or you do a survey or something like that, you want to do this, You're going to need to be able to make sure you can, use the data, use the charts you produce, the tables you produce usefully. That's why also as we go forward, I'm going to start leaning on you guys to maybe do a little coding also. By coding, I mean describing describing the variables, like the categorical variables, giving it a value label, giving it giving the numbers that are in there values and so on, so that when you create a chart, it just doesn't say 1 and 2, right? It says male and female or whatever it represents. And the title, the graph, has useful information in the description of what's in the graph or the chart, right? So that you can use it, so it'll be a bit more useful for you. Okay, so aerobic and non-aerobic sports. Okay, so let's go up here to analyze, to descriptive statistics. Okay, let's see if we can get away with this time. In the meantime, while that's working on that, I'm going to download this. I'll replace the one that's on my desktop. See, here we go. See what I've done there? I replaced the variable with numbers. If we go to the variable view, you'll see, actually, I can turn edit, I can go to view, and I can turn the value labels off. So you can see I've replaced, I made a judgment about the sport and called it either aerobic or non-aerobic. And this first one was aerobic, second one was non-aerobic, and so on and so forth. If we go to, I'll turn this back on. And if we go to the variable view, you can see the coding. So sport, values, 1 is non-aerobic sport, 2 is an aerobic sport. So we've identified it, even though it's coded as a 1 or 2, we've identified it for SPSS as non-aerobic or aerobic. So from now on, if we create a chart or a table, it'll use those values instead of the number 1 or 2. Okay, so let's go ahead and solve this. Analyze, we don't have to necessarily be in the data view. Analyze, this, what did I ask for again? I asked for, oh, I know, descriptive statistics, descriptives, except this time I am going to take, whoops, analyze, descriptive statistics, explore, and I'm going to move BMI into our variable box, our dependence box, and sport into our factor list. And now it's going to break it up into the different values for the categorical variable sport. Click OK. And it will automatically make us a box plot, side-by-side box plot. There's our side-by-side box plots. So the BMI of the girls that take place in aerobic sports is lower. The median is lower. This represents the mean, not the mean, but the median. The 25th percentile, 75th percentile. The lowest value, the highest value, similarly lowest value, highest value, median, 25th percentile, 75th percentile. What's this value up here? Why is there a circle with the number 26 up there? What's that all about? That's an outlier. That is a person whose BMI, who happened to be in the aerobic group, but whose BMI was more than 1.5 times the difference between the median and the 75th percentile. And that is just something, that's a rough calculation that SPSS does to determine whether some value is unusually different. And you could change that criteria. You can make it any criteria you want. That's just the default one that SPSS uses. So notice that this BMI is 31, roughly 31, and the range of all the other girls that are in the aerobic group is 19 to 27. So SPSS made the judgment, maybe that's an outlier. I'm going to show it to you there as an outlier. Then you can make a judgment as to whether to include it with your data or if there's a reason why you shouldn't be included. Maybe she should have been identified as non-aerobic, right? Then what is the reason for that? Why is that so different than all the other values. So it gives you a chance to examine it and figure it out. Okay, and the 26, if you go back to the data file, that would be the 26th person, 26th subject, 26th line in your data file. Okay, so, and let's see, we also have all of the various statistics, descriptive statistics, mean, standard deviation, range, quartile range for the girls that took part in the non-aerobic sports, and separately for the girls who took part in aerobic sports. So that's basically what we want. And then we can highlight one of these, copy, and paste it into a Word document. Now, how about, do you guys use Macs? Anybody here use the Mac? Yeah. Yeah. Have you had any issue copy and pasting?
I do what you told us from there to not just copy paste, but go through.
Yeah, use some sort of capture program or something like that, like Grab. Oh, export. Okay, to an RTF file.
Yes.
Okay, yeah, that's like a Word document. What's that? Oh, the RTF. Oh, good. Okay, I'm glad that's working. Right. Yeah, there's a couple of things you could do. It's a bug. It's a weird bug between SPSS and the Microsoft version of Word, right? And the deal is normally you could copy and you could go in and paste, and it would normally paste. That's an image or something like that. In fact, you can say copy, go over and say paste as or paste special, and then you'd have a choice of pasting it as a text file, as a formatted text file, not matrix, as a image, as a picture, as and any number of formats that you want to paste it in that. Unfortunately, that for some reason that bug, and between Microsoft and IBM, we little people, it's not important enough for them to fix it for us little people. And it's been hanging around. That's been a problem for a while. So at any rate, the other thing you could do besides, you could say save as, if you go, matter of fact, I'll go up here. The export. Export is a web report, just the export. Export. And if you notice that the default is to save it as an RTF file. That's called a rich text file, right? And that is basically a Word document. Okay, so you could save it as a rich text file, and I think it'll preserve most of the data, the charts and graphs that you might make. The other thing that you can do is that in my version, this is an older computer, so I've been upgrading it, but there are still some legacy programs on here. Like there's a program on here called Grab, and it might be in your utilities folder. If you go up to, let's see, if you're on the background here, if you go up to Go from the desktop, go to utilities, it might be in there on your computers, but it might not. What you can do is use Grab, and when you start Grab comes up, and Grab, you can capture a selection, a window, a screen, or a timed screen. So you can just say selection, and you can just highlight this whole thing and capture it as an image. I could then save this, save. It'll come up in a second. You can save it as a JPEG, a TIFF, or a PNG file. And then you can also go into preview and convert it to a PDF file or something like that. Well, not sure. That's particularly more useful. So you have that option also. And there is another way of doing this, and that is, I can never remember these key sequences on Mac. Shift Command 3. Nope, that's not it. Shift Option Command 3, 4. There is, yeah, there's two. There's one for a screenshot and one for capturing a section of the screen. So it's the same thing as all you have to do is use the shift. Yeah, shift. I was trying to get that. Maybe I probably made a screenshot there without realizing. Yeah. Let's see. Mac. Keys. Capture. Screen. Selection. Captures. Mac. Oh, wait. Sure if I use the screen capture. Take a look. Let's see. Why can't they just say it instead of making me read this whole thing? A portion of the screen. Command Shift 4. Let me try that. See if it still works. Command Shift 4. I look, it turns into a cursor. Okay. And now, bing, does the same thing as that grab program does. Except I think it just dumps it on the desktop. It doesn't give me any option. I think, right? Because I didn't see anything come up after that. Okay. All right. So let's look at the next problem here.
Hello?
While I'm at it, well, let's look at the next problem. I'll look at the desktop. It went somewhere. I think it's either in the documents or the desktop. Okay, let's see.
Hello?
So we got that done. Heights of 10-year-olds, regardless of gender, closely follow a normal distribution with a mean of 50. This also raised a few issues. Heights of 10-year-olds, regardless of gender, closely follow a normal distribution with a mean of 55 and a standard deviation of 6 inches. Use this distribution in following questions about height. What is the probability for that a randomly chosen 10-year-old is shorter than 48 inches? Well, how would we do that? So we have the population mean is 55. Population standard deviation is 6 inches. So we're dealing with a population here, and we're talking about an individual from that population, not not central limit theorem when we're talking about a lot of about repeated samples. What is the probability that a randomly chosen 10-year-old is shorter than 48 inches? Well, that's going to be x 48 minus 55 over the standard deviation, which is 6. So for that'd be 7 over 6, which is about a z-score of negative 1.1. So we'd go to the z-table, look up a z-score of negative 1.1, and it'll probably be about 14%, 0.14, somewhere in that area. Okay? What is the probability that a randomly chosen 10-year-old is between 60 and 65 inches? Okay, so let me just pull up this. I'll do this one. Okay, so here's our normal distribution. The mean was, what did I say the mean was? 55. And we're looking, and the standard deviation, sigma, is 6. And we're looking for 60 and 65. What was it? Was it 60? 60 and 60. So they're both up here. 60 and 65. We're looking for the percentage of 10-year-olds that are in this age range, right? Well, what we can do is for 60 and 65, we can calculate z-scores. So the z-score for 60 z-score is going to be equal to the value minus the mean over the standard deviation, which for 60 is going to be 60 minus 55 over 6 is going to be 5 over 6. Okay, and what is that? What is 5 over 6 anyway? What is it? 0.83. 0.83. And for 65 minus 55 is 10 over 6, which is equal to 1.667, right? Something like that. Am I right about that? Yeah. Okay, 4.6, yes. And since the z table is only going to have 3 digits, I can make that 1.67. So I'm going to go to the z table. Okay. And for a z-score of 0.83, positive 0.83, where'd it go? Come on, come back. Positive 0.83, 0.080123, 7967.7967. So the area from here down is 0.7967. And now we're going to find the area from here down, which is 1.67, 1.6012345670.9525. Okay, so 0.9525 minus 0.7967. Okay, I wish I had written that in a way I could read it. 9525 7967. Okay, see you see old school math here. Right? I'm sure you guys all took new math, so like you don't do this way anymore. So 11, this is a 5. I carry the 8, at 14, 5, 8. This is 0.155. So we take this area, which is about 80%, subtract this area, we take this area, which is 95%, subtract this area, which is 80%. We're left with roughly 15% between them. In fact, the actual area is 0.1558. And that is the percentage of 10-year-olds that in this population would be between those two heights. And that would also be the probability that if we picked a random 10-year-old, that he would be in that range of heights. Okay, and the next one is the one that really, I think, confused a few people. The height requirement for the Batman ride at Six Flags Mountains is 54 inches. What percentage of 10-year-olds cannot go on this ride? Aha, very interesting. So this is a little bit different. Okay, so let's take a look at this one. Okay, same distribution. Okay, here's our mean was 55, and our standard deviation was equal to 6. And okay, so we are asked the height requirement for at Six Flags Magic Mountain is 54. What percentage 10-year-olds can't go on this ride? Actually, it's not that complicated, right? Yeah, this is not that complicated. 54 inches, right? 54 inches. So we would calculate the z-score for 54 inches, which would be 54 minus 55, which is 1 over 6, negative 1 over 6. We would find the z table for that. And this is the percentage of 10-year-olds that can't go on the ride. It's the next one that I think caused some problems. Oh, 54. Oh, 54. Oh, well, first of all, you only use whole numbers for binomial distribution, right? This is continuous. So you need to stick with the 54. Even, yes.
So the answer to that was 43.
Right, that sounds right.
Right. I put in 43 as in.
Oh, and it didn't take it?
No.
Okay, I'll have to check it out. 40, you got 44? It should accept both. Okay, I'll check it. We'll take a quick break here in a minute, and I'll check it. And then we'll move on to this week's stuff. And I'll check. In the meantime, I'll also check it. Okay, so we have that. Okay, let me see what happened here. I lost it. Okay, let me go back here. Just want to get to the last question. There was one where you had to use the z table, I think, in reverse. Cannot be taken. Did I just use up my opportunities to take it? No, here it is. Okay, hang on a second here. No, that's it. Usually I ask another question that's a little bit more usual. Like, in other words, I might ask you, what height is 10%? Yeah, it was on the homework. Yeah, I did it on the review, and it's on the, I think it was a question like that on the homework. Okay, and the Venn diagrams, is that where we end up with this? Well, it's a longer test than I thought. Okay, so Venn diagram. Okay, so what are we looking at here? This is just B, right? This is just B. B. This is A union B. Could be either one, A or B. This one it's A, but not B, right? So it's A and union, A in the intersection, not B. In other words, it's got to satisfy both those conditions. Intersection means it's got to satisfy both conditions. Union means it could satisfy either condition. So we want it to be A, but we want it to be not B. So that would be A intersection not B. So that grayed out area represents the area that is both at the same time A and not B. That's why this area is not included, because it doesn't, it includes B. Heights of major soccer players are normally distributed, mean 69 and standard deviation 3. Use the empirical formula. What is the probability of randomly select the player between? So we've done this. I'm not going to go over that one again. Male players are normally distributed. Mean is 69. Oh, I see somebody here. Yes, I did the same thing, but the sports section is not showing aerobic. You must have used an old version of the file. There might have been one from a class or something like that, rather than the one that was on the exam. That's what I think. That's probably what I think happened. I'm answering the question on mine. Yes. Let me just get through this quickly here. The heights of male, okay. Heights of male soccer players using statistical phone. There's probably random soccer players. So, okay, this again, more the same. Male soccer players, if you take repeated size, if you take, this one's a bit different. Heights of male soccer players normally distribute a mean 69 inches and a standard deviation of 3 inches. If you take many repeated samples of size 36, you would expect the means of these samples to produce a new distribution with the same mean as the population. In other words, the population mean is 69, okay? And so we would expect our sample means to average, if we did it repeatedly over and over again, to on the average get a mean of 69. However, the variability is going to be slow. What would you expect the standard deviation of the repeated samples of size 36 to be the standard error? So it would be 3, the standard deviation of the population, over the square root of the sample size, which is 36 squared is 6. So 3 over 6 is going to be 1/2. Okay, I guess that's it. Okay. 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 Junior, email me about that. Okay, maybe I can help you out with that. Maybe I can do something about that. All right. Make sure you put PH750 in the subject line so I don't miss it. Okay, so let's move on. Well, first of all, okay, let's move on. Let's take a break. Let's take a 10-minute break, and then we're going to move on to a new topic. We're going to move on to the t-test, or the we've talked a little bit about the t-distribution. We started to, but now we're going to apply that. Okay, so guys online, I'm going to pause the recording, and I'm going to pause the screen.
This conference will now be recorded.
Okay, so we already started talking about the central limit theorem. The idea that if we took repeated, so let's have a population, and the population, the mean of that population is, say, 80. And the standard deviation of that population, notice I'm using Greek letters because I'm talking about parameters, mean and standard deviation of population. Sigma, the standard deviation is equal to 10. We know that if it's a truly normally distributed population, we know a lot about the way that the individuals, the subjects, the scores, the values in this population are distributed. Like, for instance, we know that roughly 95% of the values in here are between 2 standard deviations below and 2 standard deviations above. So in other words, between 60 and 100, right? We know that because we understand the nature of normal distributions. Okay, so now if I took repeated samples of size 100 from this population, and the first time I took the sample, well, I wouldn't expect to get the mean of a sample of size 100. I wouldn't expect to get a mean that is like 59, would I? I mean, it's rare for me. Only 5% of the time would I randomly pick one individual that had a value below 60, right? Or above 120. There's only 5% outside of that, right? So it's rare for me to pick one individual. For me to take a sample of 100 and get 100 that averaged under 60, very unlikely. my sample of 100 people is probably going to be very close to 80, a lot closer than the way the population is actually spread out. In fact, the central limit theorem tells us that if you took repeated samples of size 100 over and over and over again, and took the means of each one of those samples, mean 1, mean 2, mean 3, mean 4, and then created a new distribution, that distribution would have a mean of 80. Half of them would be below 80, half of them would be above 80, but they'd be much closer to 80 than the population in general. Okay, and how close together? Well, the standard error, the standard deviation of these repeated samples is going to be equal to the standard deviation of the population over the square root of the sample size. In other words, 10 divided by the square root of 100, or in other words, 10 over 10, that's equal to 1, right? So 95% of the sample means would be between 2 standard deviations above and 2 standard deviations above, which in this case would be 78 and 82. It's a new distribution, but it approximates the mean of the population, but it's much narrower. Now, if the sample size had been 25, then the standard deviation would have only been 10 over 100. It would have been 2 instead. The standard deviation or the standard error of these sample means would have been 2. So in that case, 95% of the results would have been between 76 and 84. So the sample size impacts how this distribution looks. This is how we decided what our 95% confidence interval was, because we decided that our 95%, let's say I took a sample of size 100, our 95% confidence interval would be X bar, whatever our sample came out, plus or minus 1.96, because we know our standard deviation. In all of these cases, we know our population standard deviation, times our standard error. And our standard error would vary based on the sample size, sigma over the sample size, right? So standard error varies based on that sample size, and that affects our confidence interval. Well, that's all swell, right? That's very nice. And let's say I want to calculate a confidence interval. Let's say we took a sample from this population, a sample of size 121, and actually I'll say sample size 25. From this population, sample that population, and we got a mean X bar of 86, I'm going to say 82. Okay, we don't know the population mean. I just told, I'm going to say that we know the standard deviation of the population, but we don't know the sample mean. So the population mean. So my sample mean came out to be 82. So now I want to calculate a confidence interval for the true population mean, which is 80, but we don't know that, right? So what would that be? That would be 82 plus or minus 1.96. Why 1.96? Because that represents 95% of the possible results from the z-table, times the standard error. Well, standard deviation, sigma over the square root of n, standard deviation is 10, square root of the sample size is 5, so our standard error is equal to 2. So our 95% confidence interval would be 82 plus or minus 1.96 times 2. I'm just going to, for our purposes right now, say 2 times 2 is 4, so it would be 78 to 84. So we're 95% sure the true population mean is between 78 and 84. Okay, that's pretty simple, right? No problem with that. But now let's say that I don't know what the standard deviation of the population is. I don't know what the population is. So I'm going in blind. I have no idea what the population standard deviation is. I'm going to say that I sample, let's say I sample 36 people, right? And I'm measuring blood pressure. Okay, so I sample 36 people from a population, randomly selected from a population. Take a sample size of 36. And I find that the mean for that sample, X bar, is equal to 84. And I find the standard deviation. Notice I don't use sigma now, because this is the standard deviation of the sample, right? Standard deviation of the sample is, let's say it's 12, okay? So now, say to myself, okay, great. So now I want to use this information to calculate my 95% confidence interval for the true mean blood pressure, right? The true mean blood pressure for this population. Well, my sample is 84. My standard deviation is 12 for my sample. Both of these approximate what the population looks like. That's why we sample, because when we take a sample, we're hoping to get something representative of what the sample. There's a certain amount of error involved because we're not sampling the entire population. We're only sampling a small part of it, but we can use this generally to predict what the population is like. So this approximates sigma, and this approximates mu. Okay, so now I want to actually pin this down more. I don't want to say it just approximates it. I want to be able to understand what's the probability that I'm close to the population mean. So the way we do this typically is we use something instead called confidence intervals. So I'm going to calculate it. Given this information, I'm going to calculate a confidence interval. So X bar plus or minus 1.96 times the standard error. Okay, so now what's my standard error equal to? My standard error is equal to sigma over the square root of n. Okay, what is sigma? Do we know what sigma is? No, we don't. Do we have something we could substitute for sigma that approximates the standard deviation? So it's 12 over the square root of 36, which is 6, is equal to 2, right? So we substitute the standard deviation of the sample for the standard deviation, for the sigma of the population, standard deviation of the population. Okay, so I'm going to go back over here. I'm going to look at this. I'm going to say to myself, well, this rule, this is the rule here, but I use standard deviation instead of sigma. I've introduced an extra layer of uncertainty here, right? So by using the standard deviation instead of a known population standard deviation, I need to adjust for that. So what we're going to do instead is we're going to use X bar plus or minus the t-value. Did we talk about the t-value before? Okay. The t-value times the standard error. So what does the t-value represent? The t-value represents a distribution that's based on the sample size. Each individual sample size has a different t-distribution. So 95%, the extra uncertainty that we've introduced, let me turn this thing off. The extra uncertainty that we've introduced here is going to make its place in the t-distribution. So the t-distribution for a small sample size is going to be wider than it is for a normal distribution. So 95% of the sample means, if we took repeated samples of size 36 in this case, 95% of them would be further out from the mean. In other words, a bigger z-score, we're going to call it a t-score, it's going to be a wider area out, wider z-score out than it would have been if we had known the standard deviation. So the t-score that we're going to use for a 95% confidence interval is going to be larger than the z-score would have been, larger than that 1.96. And that's going to accommodate our extra error in using the standard deviation instead of population sigma. So I'm going to go in here, I'm going to say, let's see the t-table. Address the t-table. Now, I mentioned that there's really a different distribution for every different t-table. Okay, so we would have to have, if we wanted to have two samples from 0 to 200, sample size from 0 to 200, we'd have to have 200 pages. Actually, if we had, like we'd have the z-score, if we had the negative ones and the negative t-scores, positive scores, We'd have to have 2-page fees. We'd have to have a book with 400 pages in it. Well, we're not really that interested in all of the possible t-scores. We're really mostly interested in the t-values that represent 95% certainty, 99% certainty, and say 90% certainty. So for our confidence interval, instead of using 1.96, we need to use the t-value that corresponds to a 95% confidence interval, 2.5% outside of either 2.5% tail on the left and on the right side. This one says right, but it's symmetrical on the left also. And with a sample size which is appropriate for the analysis that we're doing. The analysis that we're doing is for a sample size of 36. Well, instead of using sample size, the t-table uses degrees of freedom. And the degrees of freedom are equal to the sample size -1. So in our case, 35. So I'm going to see here if we have a value for 35. Well, we don't. We actually don't have a value for 35. We have 30, which is for 95%, it's 2.04. And for 40, it's 2.02. Now, there's a couple of ways I could deal with this. One way I could deal with it is just take the larger number. It's more conservative, right? The 2.042. Or interpolate between the two of these. 2.04, 2.02, I could say 2.03, right? That's another possibility. Or I could actually go to the Excel and there's a t distribution. You can put in there the degrees of freedom and the sample size, and it will give you the critical value of t, right? So I'm going to just go in between these two for our purposes right now, 2.03. So instead of using 1.96, I am going to use 2.03. So X bar is going to be 84 plus or minus 2.03 times our standard error, which is 2. Is this going to be wider or narrower than if I had used the z-score? Opinions? It's going to be wider, right? We're using a bigger number, we're multiplying by a bigger number, so it's going to be wider than it would have been if I used 1.96. So it's going to be 84 plus or minus 4.06, right? So on the high end, it was going to be 88.06, and on the low end, it's going to be 79.94, I believe, right? That's my 95% confidence interval because I use the t-value. Okay? And I need to use the t-value. Why do I need to use the t-value? Because I don't know what sigma is. If I knew what sigma was, I could use the z-square. Since I don't know what sigma is, I got to use the t-value. Well, I'm gonna look at this from another perspective. Okay, actually before I move on to this, let's say I had another population. Let's say that I sampled 96 females. This is for blood pressure for female residents in a nursing home. And let's say that I knew that, you know, the nursing homes, this is the whole nursing home system. So thousands, tens of thousands of people in the whole nursing home system. I randomly sampled 36 females. And, you know, the males, there was a separate program where they sampled all of the males. And I know that the mean for males is equal to 78, for argument's sake, right? Well, my confidence interval says I'm 95% certain that the true mean for females is between 79.94 and 88.06. It's between, if I repeated this over and over again, 19 out of 20 times I get this. I would capture the mean within these things. Not 100%, but 95% certain. It's between these two values, the true mean for females. Well, can I say with 95% certainty, in other words, with less than 5% chance of being wrong? That's called having an alpha error of 5%, right? Less than 5%, right? And what does that mean? That means that we're willing to accept less than 5% chance of being wrong when we make a conclusion about whether two means are the same or not. So in this case, would you feel comfortable saying that you're 95% certain that the mean blood pressure for females and males is different? You know that the males are 78, you're 95% sure the females are 80 to 88. So how do you feel about that? Could you say with 95% certainty? Seems like it, right? Okay. Well, what if I had told you the mean for males is 81? Would you be 95% certain now? Well, no, because it might be the mean for females might actually be 81. It's between you're 90% sure it's between 80 and 88. That means that you can't be. That means that there's more than 5% chance that it could be 81. 81 is within that interval, right? So we want to make sure that what you're comparing it to is outside of that interval before you say that they're different, okay? With 95% certainty. Well, in statistics, we really don't use this quite this way. We do it a little bit differently. We look to see, well, I'm gonna start again here. I'm gonna open this up again. And I'm going to tell you that sample size is 36. Our mean for females is, what did I say it was before? 84? 84. Our standard deviation is equal to, I forgot what I said. 12? Yeah, that sounds right. Okay, yeah, that goes along with 36, yes. Okay, and I'm going to ask you now, let's outline a hypothesis here. And when we create a hypothesis, right, we say to ourselves, let's start out by saying that two populations have equal means. In other words, I'm going to say the mean for males happens to be 78. Remember, we had decided that that's outside of our confidence interval. We're not going to use it that way right now. So we have a sample, and we're comparing it to a known mean for another population. This population, we don't know what the mean is. We don't know what standard deviation is. All we know is we took a sample of 36, found the mean in the sample is 84, standard deviation is 12. The other population, we happen to know that the mean is 78. And we want to know, can we say with a good level of certainty, with 95% certainty, that these two populations have different mean blood pressures? In other words, their blood pressures are different. Okay, so we're going to start out with our hypothesis. Our hypothesis is going to start with the assumption that both populations have the same mean. In other words, the mean blood pressure for females is equal to the mean blood pressure for males. Okay, that's it. That's simple, right? Okay, so now I'm going to say, what would my alternative to that be? Okay, the alternative to that would be the mean blood pressure for females is not equal to the mean blood pressure for males. That's actually what I'm trying to prove, isn't it? That they're different. Usually we're trying to prove a difference. We're trying to prove that a drug works better than a placebo, that an intervention improved an outcome, made the people that had the intervention had better outcome, people without the intervention, that a diet system works, and so on. We're usually trying to prove the difference, but we start by making the assumption that the means or the two populations are the same. Okay, so we're going to call that same the null hypothesis, right? Null basically means none or no difference. Okay, we're going to call this hypothesis, this formula, the alternative hypothesis. Okay, that they're different. Null hypothesis that they're the same, alternative hypothesis that they're different. And we want to make sure that before we reject the null hypothesis, we want to make sure that there's less than 5% chance that the null hypothesis is true. In other words, we want to say that our alpha error, our chance of rejecting the null hypothesis, if it's true, is less than 5%. Okay, so how do I go about doing this? Okay, so now I have to say to myself, well, how big is the difference between these two? Well, in one case we have 84, in the other case we have 78. Well, in blood pressure terms, they're 6 apart. whatever that is, millimeters of mercury or whatever. They're 6 apart, right? However, the variability ties into this whole thing. So I want to be able to say that 95% certainty means about 2 standard deviations. So I want to be able to say with 95% certainty, 2 standard deviations different, that these two are really different, that I wouldn't expect to have an outcome of 84 if the population for females had the same blood pressure as for males. That would not come up that often, 84. Okay, so how am I going to do that? Well, I'm going to say to myself, let's see. I'm going to say that the number of z-scores, number of standard deviations that these are apart, are equal to x bar minus mu, the difference between the two, over the standard error. Okay, so I got a problem with this stuff. The standard error, I can calculate that. That's equal to 12 over the square root of 36, which is equal to 2. I can calculate that. But did I use sigma here? No, I used, so this is not really z. This is actually t, right? So I need to find the t-score, the number of t-scores apart that these two are, is t is equal to x bar, which is 84, minus mu, which is 78 for the male population, over the standard error, which is equal to, well, it's not 2, is it? I really can't, I really can't, oh, excuse me, it is 2. It is 2, right? Right, and that's going to be equal to, that's 10 over 2 is equal to, oh, I'm 78, I'm sorry. 6 over 2 is equal to 3. So I am 2 t-scores apart with these two means. How far apart do I have to be for the sample distribution for a sample size of 36 with a t-distribution for a sample size of 36 for me to be able to say with 95% certainty I can reject the null hypothesis? Well, that t-score that we're interested in, that's called the critical value of t. And that's based on the sample size, right? So what did we say our sample size was for a sample, for what a t-value was for a sample size of 35, 36? It's going to be 35 degrees of freedom, right? It's going to be 2.03. So our critical value of t that we need to exceed the distance apart in standard errors that these have to be, our critical, t critical, is equal to 2.03. So in this calculation, have we exceeded our critical value of 3? Right? What is our t critical? Excuse me. Did our calculation t equals 3, did it exceed our critical value of t, which is 2.03? Are these more than 2.03 standard errors apart, which is what our critical value is for a 95% certainty? 3 is bigger than 2.03, right? So what that tells us is that there's less than 5% chance that you would get this big a difference between these two means if the null hypothesis were true. So since there's less than 5% chance that we would be wrong, we reject the null hypothesis and we accept the alternative hypothesis. This is called a single sample t-test. I'm going to do another one. Okay. So in this one, I have I'm comparing cheesemaker A to cheesemaker B. Cheesemaker B tests the fat content of all of the cheese that he makes, and we know that the mean fat content for his per pound per pound of cheese that he makes is 14.2 ounces per pound. That's the fat content in his cheese. Cheesemaker A, he doesn't test every wheel of cheese that he makes. But we take a sample of size 25 and we pull a core out from his cheese. We analyze those, and the average amount of fat, ounces of fat per pound of cheese in those 25 samples turns out to be, let me make a number up here, 12.9 ounces. Okay. Now, we take the standard deviation for those 25 samples, and the standard deviation turns out to be, let's see, turns out to be 4 ounces. Okay, that's the standard deviation. Okay, so now I want to decide whether cheesemaker A and cheesemaker B, the amount of fat in their cheeses is the same, or is it different? In fact, I'm really trying to prove that cheesemaker A's cheese doesn't have as much fat as cheesemaker B, that they're different. But I start out with the assumption that they're the same. So my null hypothesis, let's develop our hypothesis here. What is our null hypothesis here? Right? The mean, what? The mean for cheesemaker A, mean fat content for cheesemaker A, is equal to the mean fat content for cheesemaker B. What's our alternative hypothesis? That they're not equal. Mean A does not equal mean B. Okay? Okay, so how am I going to compare the two of these? I compare the two means using a test called the student's t-test. We'll get more into, next time, we'll get in more into a little bit of a regular lecture about student and t-test and its origin and so on and so forth. But for right now, let's work through an exercise doing this. Okay, so the value, so how far apart are these two means? Well, my t-score is equal, and why am I using t instead of z? Because I don't know the population standard deviation for either of these, and my sample is small, it's only 25 people. So the t value is equal, the number of standard errors apart that these two means are, is equal to, it's equal to, let's see, x bar minus mu over the standard error. Okay, x bar is 12.9 minus 14.2 over the standard error. So what's the standard error equal to? Standard error is the standard deviation, or sigma or standard deviation, divided by the square root of the sample size, which is 5, and that's equal to 0.8. Okay, so I'm going to divide this by 0.8. So my t value is equal to 14.2 minus 12.9 is negative, let's see, 1.2, 1.3, divided by 0.8. So my t value is equal to 0.8 into 1.3. That's 1 and negative 1 and 3/8. 1 and 5/8. What is negative 1 and 5? That's 1.625. If my carpentry works right. 1.625, right? So I'm not going to worry about that negative positive sides. That's a number of standard errors apart. These two means are. Okay, so now that I know that t is equal to 1.625, is that big enough for me, big enough difference between these two means and standard errors for me to reject the null hypothesis? What do I need to know before I can reject the null hypothesis? What do I have to know about t? I have to know what the critical value of t is. Then I need to be 95% certain that I can reject the null hypothesis. And what is that value of t based on? It's based on the sample size, right? So I have to go to the table to find out the critical value of t. And here's the table. And degrees of freedom, how many degrees of freedom am I looking at? 24. And the critical value of T is 2.064. So critical value of T is 2.064. And the value of T I calculated was 1.625. Have I exceeded my critical value of T? No, right? It's small, 1.6 is smaller than 2.0, right? 2.064. I haven't exceeded my critical value of T. My two means are not far enough apart for me to be 95% certain that the population means are different. So what do I do now with my null hypothesis? What do you guys think? I failed to reject it. That's it. You don't say you proved it. You haven't proved it. You just failed to reject, right? Because the t-value, the number of standard errors apart that your two means were, is not enough to exceed the critical value that you needed, which was 2.06 standard errors apart.
So the critical value is lower than what we just figured out.
If
When we reject non-hypothesis.
If the T, right, exactly right. If your T score that you calculated exceeds the critical value of T, that means that they're so far apart that that outcome would occur less than 5% of the time. So you can reject the null hypothesis. If your T score that you calculate is not bigger than your critical value of T, well, then it's not less than 5% chance that you would get that outcome for the null hypothesis, that the means would be the same. In other words, maybe it's close, maybe it's 6% chance of that happening, or 8%, but it's not less than 5% chance of not getting such an extreme outcome.
We fail to reject non-hypothesis. Does it mean we accept alternative hypothesis?
No, you'll only accept the alternative hypothesis if you first reject the null hypothesis. See, they both can't be true. In other words, you can't accept this until you've rejected that, right? And if you don't have the evidence to reject it, all you say is, I failed to reject the null hypothesis. How do I got what? 2.064, sure. Okay, so what's the sample size here? Sample size here is 25, right? Okay, so sample size is 25. That sample size and the level of certainty we want that alpha is equal to 5%, right? The level of chance of being wrong. We want less than 5% chance of being wrong, which is kind of the same thing as saying we want to be 95% certain. We go to the t-table and we look up for 24 degrees of freedom, n minus 1. We look up for 24 degrees of freedom, that's this line across. We look up what the t-value has to be for us to be 95% certain. In other words, less than 5% chance of being wrong if we reject the null hypothesis. And I go down here to 24, and it's 2.064. So that's the number that our t-value has to exceed when we take x bar minus mu over the standard error. When we calculate how many t-values apart they are, it has to exceed that number. So if it's a small sample, like a sample size of 5, then degrees of freedom equal 4, the t-value, the critical value of t is 2.776. For a sample size of 2, right, which is 1 degree of freedom, it would have to be more than 12.7, right? It gets bigger and bigger and bigger. Notice that if you have an infinite sample size, in other words, if you know the entire population, means you know the population standard deviation, you can just use 1.96, which is originally what we started with when we used the z-score, if we knew the population standard deviation. Right? So that's basically how you would use it. Would you necessarily do it by hand? Well, if all I gave you was this, yes. But if I gave you the data set, yeah, that's another story. So let's take a look at doing this using SPSS. If I can find it. Okay, let me close this. And let me get this out of the way. Yeah, let me use this. Oh, got the wrong file. Okay, I'm going to open up this. There's a data set in here. I'm going to open this one. Let me see. Here's an SPSS data set. See how successful I am at opening this. And I think it goes with our lab exercise here. Okay, so here's a series of numbers. I just simply called it X. A variable is called X. And okay, let's see. These are the same numbers here. 5, 7, yeah, same numbers. Okay, so here's a problem. We take a sample of size 9, right? These 9 numbers. We take a sample of size 9 from a population, right? So here's our first population is A, right? Size 9. The standard deviation, here's the numbers here. We can calculate a standard deviation, and we can calculate a mean for this sample, right? So I want to compare it to a population that has a known value of 8. So how would I do this using Excel? Let me open up the Excel version of this file. So I'll do this by hand first. Where'd it go? Okay. So here's a sample size 9. So the mean of this is population. This is a sample taken from population X, and population Y. We know that the mean is 8. We know that the mean is equal to 8. Okay. So let's take a look at our sample from population X, whose mean we don't know. The average, the mean for this sample is equal to, whoops, please mean, average is equal to 9.88. Okay. The standard deviation, that's X bar, the standard deviation for this sample is about almost a little under 3. Okay, so now I want to determine what is my null hypothesis here. My null hypothesis here is that the mean for population X is equal to the mean for population Y. Okay, and my alternative hypothesis is the mean for population X does not equal the mean for population Y. Null and alternative hypothesis. Okay, so how do I prove that the mean of this population is different from the mean of this population, given that I really don't know the mean of population X? All I know is X bar, the sample mean, right? So I'm going to go ahead and calculate that. I'm going to use the formula we just used was, right, the value of t, the number of standard errors apart, is equal to the difference between the two means, X bar minus mu. See, the only thing I know about the first population is X bar. I don't know mu, but I do know mu for the other population. The difference between those two means divided by the standard error. Now, the only problem here is that I use t because I don't know the population standard deviation. Normally, I would say I would use my critical value would be 1.9. I would use z and look for the difference between these to be 2 standard deviations apart. In other words, bigger than 1.96. So instead, my critical value of t is based on my sample size. Okay, and what is my critical value of t going to be? Anybody got a t-table open now? Tell me what my critical value of t is. For a sample size of 9, that would be 8 degrees of freedom. And since our level of uncertainty we're willing to accept is 5% or 95% confidence, 8 going across here, 95% is 2.306. So my critical value t is 2.306. So I'm going to go ahead and calculate what t is equal to. It's equal to x bar minus 8, right, parentheses, over my standard error. What's my standard error equal to? Well, I didn't calculate that yet, did I? Let me do that first. My standard error, right, is equal to the standard deviation, that's all I have on a population, divided by the square root of the sample size, which is 3, is equal to 0.9781. So what is t equal to? T is going to be equal to, it's going to be equal to x bar minus mu, which is 8. I'll put those in the parentheses. Divided by the standard error. Okay, the number of standard errors apart. And what's that equal to? That's equal to 1.93. So t is equal to 1.93. So what's t critical? What's the value it has to exceed in order for me to reject the null hypothesis? 2.03. Can I reject the null hypothesis? Yes, no? Can I reject it? No. You guys agree? No. Why can't I reject it? Because the two means are not far enough apart for me to get a t-score that's bigger than 2.3, which is what I need for this sample size. Okay? Now we're going to repeat this exact same thing using SPSS. This is the same data, and unfortunately I can't blow it up for you, but hopefully be able to. Thank you online there. Great, thank you. I appreciate that. Okay, analyze. Okay, so what am I doing now? What's going on here? What kind of test am I doing now? Let's see. Not descriptive statistics. I'm comparing means, right? What kind of comparison of means am I doing? I'm doing a one sample t-test. I'm taking a sample from a population and comparing it to a known mean. So there's really only one sample going on here. So I'm going to click that, and my box is going to come up here, ask me what variable I want to work with. It happens to be the variable x, and the value of the mean I'm comparing it to is 8. Okay. So I'm going to go ahead. I don't think there's anything in options that we really need to worry about. 95% interval. So I'm going to click OK. SPSS will do this operation and pull up a output table. And let's see what we wind up with. We wind up with a t-score of 1.931. Does that look familiar? That same number we got, right? Okay, 8 degrees of freedom. Okay, now, next thing it tells me is the significance. Here's the mean up here, 9.89. Okay, standard deviation and standard error. Did all the calculations we did in a lot faster, right? Our t-score, the difference between our mean and the population mean is 9.89 minus 8, right, which is divided by, and then divide that by the standard error, which was 0.978, comes out to 1.93. That's how many standard errors apart that we are. Okay, but we need that to be more standard errors apart. Now SPSS does not give us the critical value of t. What it does instead is use the t-tables that it has built into us and give us an actual number for the probability that we would be wrong if we would reject the null hypothesis. Do you remember what the level that we were willing of risk of being wrong that we would be willing to accept was? In other words, alpha. Alpha was 5%, right? So we want to see the probability of being wrong being less than 5% in order for us to reject the null hypothesis. So this significance here, that's the p-value or the probability that we could get this extreme of value in this situation. In other words, the probability that we would be wrong if we rejected the null hypothesis. And what is it? It's 9%. Is that less than 5%? No. So we have the chances we would be wrong if we reject the null hypothesis would be more than 5%. So therefore, what do we do with the null hypothesis? What do? We fail to reject the null hypothesis. Okay? I can see this is going to take a little while to sink in. It's not really not that you see what I'm doing here.
So that would say 5 point something, then we reject it, right?
Yeah, if we're 0.52, 0.6.94, and so on and so, whatever. What you mean the p-value we're talking about?
Significant detail, right?
Yeah, that's the p. The significance two-tailed is the same as what we call the p-value, or the probability of getting that extreme a value if the null hypothesis is true. Okay, or in other words, the probability, in a sense, the probability we'd be wrong if we reject the null hypothesis. We want that significance, that probability of being wrong, to be less than 5%. Okay, in order to reject the null hypothesis. Okay, so it's 9%. So we can't reject the null hypothesis. Now, I'm going to do something a little weird here. I'm going to change some of these numbers. I'm going to make this 15. I'm going to make this 12. This 10. I'm going to redo this again with different numbers. Analyze. What am I going to choose here? Compare means. That's what we're doing, comparing means of two groups. Compare means, one sample t-test because we only took one sample from one population. The other population, we know what the mean is. Take that, and I'm going to compare that to, actually, I'm going to say I'm going to compare it to the other population has a mean of 12. I'm going to say. And I'm going to say, okay. I just want to see what comes up here. Okay, what happens here? Let's see. That's even worse. We still reject the null hypothesis here. I was going for something where we could read. Let me see what the mean is here. Where's the output? Let me look at the output. Okay, the mean here was 11.78. Okay, good. I got that. I know. Analyze, compare means, one sample t-test. I'm going to make this. Actually, what is this happen for the rest of that? 11.6. Okay. See if it comes out any better. Why is this doing this to me? 11.6. One sample t-test, 11.68. Degrees of freedom. So the mean 9, 8. Standard error is that. So what am I comparing it to? Means one sample t-test. I don't know what's having such a hard time with this. Keeps doing the same. It's not changing to a 12 on my thing here. I don't know why. 11.78 compared to the 12. Oh, that's a small difference. Oh, okay. I know what I mean now. Okay. Analyze. Compare means. One sample t-test. I'm going to compare the new distribution to my original mean test value of 8. The mean of the other population is 8. I'm going to click OK. And this time, the mean of my sample is 11.78. The mean I'm comparing it to is 8. So 11.78 minus 8 divided by the standard error gives me a t-score of 5.7. Since it's a sample size of 9, remember what that t-critical was? It was like 2.3, right? Our t-score of 5 is much larger. So we reject the null hypothesis. So you would reason that in SPSS, that p-value should be less than 0.05. And in fact, it's less than 0.001 even, right? They put 0.000. It's not really zero. It's really less than 0.001. So that p-value is very low. Since it's less than 0.05, we reject the null hypothesis.